In this video, we'll look at using reduction potentials to predict whether or not a given electrochemical cell will be spontaneous. We'll look at writing these cells in line notation, and we'll look at producing the relative strength of oxidizing and reducing agents using a table of standard reduction potentials. Okay, so if we're given a reaction like this, and we want to know whether or not it's spontaneous, we're already given the reaction. So what we can do is break this out into the half reactions. So here we have the reduction half reaction for copper. Notice this is the reverse of this reaction up here. And we have the reduction half reaction for hydrogen. We listed the reduction reactions for both of them so that we could use our table of reduction potentials. In order to get them to add up to equal our actual equation, we'd have to reverse the copper reaction. And in doing that, we're going to change the sign that we find on the table of standard reduction potentials. And then we can combine these two equations, combine the potentials, and get the overall potential for this cell. So will this be spontaneous? We can calculate delta G to know for sure, but we also know with a negative standard reduction potential, we expect this to be non-spontaneous. So if we look at the calculation for delta G, and we have E naught cell is less than 0, here's our equation. So delta G is equal to NFE cell. We have 2 moles of electrons being transferred, and we get this from these half reactions here. So we see the 2 electrons, Faraday's constant, and our reduction potential, and we get a delta G of positive 65.6. So again, this is a positive delta G and verifies this is a non-spontaneous reaction. So if we wanted to turn copper into copper 2 in an acidic environment with H pluses, we would have to apply some external voltage. So it needs some other driving force to make this reaction happen. Okay, let's look at another example. So say we take a piece of solid copper and we place it in iron sulfate solution. Does iron deposit on the copper? And the answer to this would be no. If we have solid copper, that means we'd have to reverse this reaction. And so that means we would change the sign of this equation, and when we added them together, we'd get a total of negative 0.78 volts. With a negative cell potential, this is a non-spontaneous reaction. What if we did this in reverse? If we placed an iron nail in copper sulfate, well, we know the reverse of a non-spontaneous reaction was spontaneous, so we'd expect this to happen. And you can check for yourself if you look at the previous equations and put them in the correct order and add them together, you should get a cell potential of 0.78 volts. Okay, so let's do a little bit of a recap. We can look at writing reactions. So if we're given a galvanic cell, we know that it has to be spontaneous. So that means we'd write the half reactions so that the E naught cell would be greater than 0. So we'd pick which one would have to switch so that we had a spontaneous reaction. If we're given the reaction but not told whether it's galvanic or electrolytic, then we have to write the half reactions as given, see which one is reversed and change the sign of that cell potential, and then add them together. If the E naught cell is greater than 0, it's spontaneous, and if it's less than 0, it's non-spontaneous. Let's look at a little more practice. So say we have a galvanic cell where we have zinc immersed in a zinc solution, silver in a silver solution, and the following standard reduction potentials. Let's write the overall reaction. So to make this be spontaneous, we can see that the one that would run a reverse would be the bottom reaction. To make the electrons add up, we'd multiply them by 2. And so we'd get 2Ag plus zinc goes to make 2Ag plus the zinc cation. And when we reverse this, we'd change the sign, so the potential would be 1.56 volts. So when we're going to write this now, we're going to try writing it in line notation. So for line notation, we'll always write the anode, a double bar, and then the cathode. So to do this, you'll want to write the reactions out. So remember, we flipped the zinc reaction. And so this was the oxidation half reaction, that's the anode. And then the cathode half reaction, where the reduction occurs, is the silver reaction as it was written. And then when we write these, we'll always go from left to right. And so in the combined reaction, we're going to start with the solid zinc. We do a single bar to represent the phase change. So this was a solid going to the aqueous phase and becoming the zinc 2+. And then on the reduction side, we start with silver ions and then go to the silver solid. If we wanted to work backwards, say we can identify the reaction that matches this line notation. So it's always the anode and then the cathode. And so the anode is always where the oxidation is occurring. So we have to write the oxidation reaction, and the cathode is going to be the reduction reaction. And so to write the combined equation, we have to make the electrons match, so we'd have to multiply this by 3 and this by 2. So we'd get 2 Al plus 3 copper 2, going to make 2 of the aluminum cation plus 3 copper solid. You might also see another case with these line notations where we have the redox pair, so whatever reaction's happening is in the same phase. So we're still writing left to right, but since we don't have a phase change, instead of using a bar, we'll separate them with a comma. So in this case, we still have our silver anode, and so this will be our oxidation half reaction. And this is telling us that the copper is the cathode, and it's going from copper 2 to copper 1. And so we would write this reaction, would write Ag plus Cu2 plus, going to make Ag plus Cu plus. So the other question is what is the PT doing here, this platinum? And this is the electrode for this cell. So if we were to make this cell, at the anode would have our silver metal sitting in the silver solution and connecting to a wire. And then we have our copper solution. The problem is we have to get from this solid wire into the liquid where the reaction is occurring, and we don't want this reaction reacting with the wire itself. So we usually use some inert metal that won't react with things in the process, and you'll often see platinum is just there to carry electrons. Sometimes you'll also see glassy carbon. And so if we were to write it out, we'd just see our anode is silver in silver solution, and our cathode is a platinum electrode immersed in a copper 2, copper 1 solution. Okay, so we'll now look at how to use these tables of reduction potentials to determine some properties of oxidizing and reducing agents. So as a review for these definitions, say we had these two half reactions and we added them together. In this case, which would be the oxidizing agent? Okay, and the answer here is copper 2. So remember, the oxidizing agent is going to oxidize something else, meaning it's going to make something else donate electrons. So the oxidizing agent gets reduced. And likewise, the reducing agent gets oxidized. So with these equations, when we're talking about oxidizing and reducing agents, we're only going to look at reactants. And we can see that it's copper 2 plus that's getting reduced, and so that's our oxidizing agent. So if we look at this table of standard reduction potentials, this is actually also a list of oxidizing and reducing agents. If we look on the left side, everything here is getting reduced. And so everything on the left is going to be oxidizing agents. So F2, Cu2 plus, Al3 plus, etc. And that means on the right, these are all the things that could get oxidized with these potentials, and those will be our reducing agents. When you're looking at this table, because more positive potentials are more spontaneous, as we go up this table, these will be better oxidizing agents, or they'll increase their oxidizing strength. So on this given table, F2 is going to be the strongest oxidizing agent. Likewise, on the other side, since we're going to flip these reactions, if it's acting as a reducing agent, we want the most negative one to be the most spontaneous, and so these will increase going down the table. So again, if we're looking at one of these tables, the strongest oxidizing agent is going to be in the upper left. The strongest reducing agent is in the bottom right. And this is for any table of reduction potentials that has the positive reduction potentials at the top. So this will help us answer questions like this. So if we have these species, F2, H+, zinc, and lithium, which of these can oxidize aluminum but won't oxidize copper. To do this, we want to take a closer look at the table. So remember, on the left are our oxidizing agents. So if we look at the species that we have, we can check F2, we can check H+. You'll notice that zinc is on the wrong side. It's a reducing agent, not an oxidizing agent, so we won't worry about that. And we can also check lithium. So of these species, we want to oxidize aluminum, but not copper. And so in order to oxidize a species on this side, the oxidizing agent has to be higher up on the table. So if we look, anything that's above aluminum can oxidize aluminum. So the things that can oxidize aluminum would be H+ and F2. But we also have to find something that cannot oxidize copper. If it's above copper, it will also oxidize it. So F2 will oxidize both. Lithium can't oxidize either. And only H+ can oxidize aluminum, but not copper. We can look at another type of question that we can use the table to answer. And this is, would silver dissolve in a hydrochloric acid solution? So we have our silver solid, and in order to dissolve, it has to become Ag+. So in order for it to dissolve, silver has to lose an electron or become oxidized. So what we're looking for is an oxidizing agent that's strong enough to oxidize silver. So here's silver in the chart, and if we look at HCl, this will become H+ plus Cl minus. So we see H+ as an oxidizing agent is too weak because it is below silver on the chart, and Cl minus is not an oxidizing agent at all. So the answer to this would just be no. So again, the problem is telling us that silver is going to an ion, and H+ is not a strong enough oxidizing agent, and Cl minus is not an oxidizing agent at all. So it will not dissolve in hydrochloric acid. Okay, how about silver dissolving in nitric acid? And the answer to this one is yes. So remember, we're still looking at this equation. We know that H+ is not strong enough, but HNO3 dissolves to make H+ plus NO3 minus. So the H+ is not strong enough, but if we look at the NO3 minus, we can see it appears here as an oxidizing agent, and it appears above silver. So nitric acid can dissolve silver solid because the nitrate will act as an oxidizing agent to convert the silver to silver plus.